Okay, a comment then that this is the key to finding the surface area of any three-dimensional surface. Now we'll build that up in a few weeks, okay? But right now, I want you to just understand it on a single increment, because that's where people don't understand things, so they never understand why the integrals are what they are. Just follow the formulas like engineers or something, okay? And of course, that's just following the formulas is an excellent skill, okay? So I'm not denigrating it. But we want to try to understand it a little more deeply so you don't have to memorize a bunch of formulas, you just know. Okay? And again, gives you a deeper level of understanding, will tend to make a better engineer out of you. Okay. So anyhow, now we have the same picture we had before, right? Whatever rectangle you have here, if you got some function f of x, y, or some way of figuring out these altitudes, you get this picture. And if this is small enough, then this is actually a parallelogram, or very close to a parallelogram, right? So we're going to kind of assume it's small enough to give us a good enough approximation of a parallelogram. And later we might have to figure out how small it has to be to do that. But practically, we're going to usually consider the continuous case where you take the limit as the dimensions go to 0 anyway, so you can always kind of assume that this is a parallelogram, okay? Now, we have what's called a vector field, f of x, y, z, okay? Now, I'll draw you an example of a vector field, but just operationally. F of x, y, z is just some function of x, y, z multiplied by I, plus a function of x, y, z multiplied by j, plus a function of x, y, z multiplied by k. Right?
So give us the vector within the, give us the vector at any given point in a three-dimensional area.
If I have a point up here, and it could be one of these corner points, it could be any point inside here on this surface, or actually the point corresponding to any x, y down here, okay? So this is a point and let's just put it in the context of an f of x, y. Well, I actually could have done that. X, y, f of x, y, okay? Except I'm going to call this x, x star, this y, y star, this x star, and this y star, because it's a sample point within this region. So clearly, to get up to the actual surface, you're going to plug that into your f of x, y function, right? Give you an altitude. And that point might not even lie on this parallelogram, because this is a finite dimensional surface, but it's going to be close if you have a small enough rectangle down here, okay? So we're going to kind of assume this is, it's either on the surface or very close, okay? Well then, we take these coordinates and plug them in here, okay? So, and again, we're still in the context where this picture represents a little increment of the function z equals f of x, y, okay? And this is building, you know, it's getting kind of complicated, but you can sort this out, okay? I'll give you some questions that will inspire you to sort it out, or intimidate you into sorting it out, okay? You know, break it into steps for you, okay? But it's really pretty easy. It's just that this is new, so it looks a little bit funny, okay? So all we're saying is, you got your function, little f of x, y, and some rectangle down here so you can construct this thing, and you know how to do that. You've already done that a week ago. Take the cross product of these two vectors, which are easy to calculate, you get a normal vector. Now we take a sample point within here, anywhere within here, and you could use a corner point if you like. Wouldn't really matter. If you have a small enough rectangle, it's not going to change much from one point to the next, right? And you get your sample point is x star, y star. And that gives you a point up here that's either on or very near the parallelogram, or the region bounded by the parallelogram, region within the parallelogram, right? So there are 3 coordinates. Now you got this vector function, and each component has 3 coordinates, right? So you take these 3 coordinates and plug them in. X is going to be your x star, y is going to be your y star, z is going to be f at x star, y star. Okay? To get our vector that I'll just call plain old f. Okay? We've plugged in the coordinates of the points, and now we got a vector. Okay? And this vector might look like this, right? So now we have our normal vector, and our vector f well, they do make some angle that you can easily calculate, right? Just take the dot product of these 2 vectors, divide by the product of their magnitudes. Okay? And this angle determines how much of this vector tends to penetrate this parallelogram. It's like this is the direction that you threw that chalk in, okay, when you're trying to hit this thing, okay? You're over there, again, I haven't done this in camera, so we'll do this. You're over there, you know, at some distance, and you're trying to hit this. If I hold it like this, and you're throwing straight, not lobbing, right? Then you're more likely to hit this thing here than you are if it's here. And more likely to hit it here than if you're here. And this all just depends on the angle between, and to define the angle of a surface, we don't use a vector within the surface, which could go in any direction on the surface, right? We use the vector perpendicular to the surface. This is the vector that defines the orientation of the surface, right? Okay? And we've got this vector and we've got the k vector. So the angle between this vector and the k vector is the one we're going to use. That's going to be our theta, right? Well, that was our theta over here. We got a theta here too, but the k vector is not involved in this case. Okay? So right now we're trying to see how much of whatever vector penetrates the surface, right? So if its surface is like this, from over there you see less of it. You know, I can show you. Right there it is at an angle. It's going to be harder to hit. And if I hold it edge on, you're not going to be able to hit it at all unless you lob it. Okay? So we're looking at the tendency of vectors in this direction to actually pass through this parallelogram. Okay? So the component of f that passes through the parallelogram is just going to be the projection of f onto the normal vector, isn't it? Now, it's been a while since you thought about projections, so we talk about those a little bit. Okay, okay. Now, if your 2 vectors are like this, then the projection of this vector on this one is just this, right? That's what I mean by the projection. It should be clear that the bigger this projection, the more of this thing is parallel to the normal vector, and the more of it's going to penetrate. So if this is a direction from which you're shooting, the closer this direction is to the normal, the more likely you are to hit the target, isn't it? Okay, well, let's develop the idea just a little more.